안녕하십니까. 지금부터 양자 컴퓨팅 기술의 미래를 이끌어갈 중요한 논의가 진행되는 연세 퀀텀위크 2025 인더스트리 세션을 시작하겠습니다. Good morning, everyone. We're about to begin the quantum industry session, where the important discussions on the future of quantum computing technology will take place. 첫 번째 세션을 시작하겠습니다. 첫 번째 세션은 IBM 퀀텀의 Dimitris Alevras 박사님께서 mRNA secondary structure prediction using utility scale quantum computers라는 주제로 온라인 발표를 진행하시겠습니다. Now we will begin the first session. Dr. Dimitris Alevras from IBM Quantum will give an online presentation on the topic mRNA secondary structure prediction using utility-scale quantum computers. Please give a big round of applause. 큰 박수 부탁드립니다. Dimitris, you can start now.
Hello, can you hear me?
Yes.
Okay. Hi, it's my pleasure to be here with you today to share our work on applications of quantum computers to the optimization of mRNA. This work is joint work we do with Moderna, which is a leader in mRNA research. The results of this work have been published in the conference proceedings of the QC24 that took place last year in Montreal. So why mRNA? So mRNA, as probably you all know, is the way genetic information is delivered in our bodies. So basically it's the translator from DNA to the functional molecules that are proteins. It is used to direct the production of protein in humans. So basically it provides a recipe of how to create the proteins. Recently, in the past decade or so, it has been emphasized and pursued, the research has been emphasized and pursued to expedite, to use mRNA to expedite and optimize drug discovery. And that's due to its high degree of designability that allows you to target, to discover drugs for large populations, as we evidenced in the creation of the COVID vaccine a few years ago, and also for personalized medicine to target particular individuals for their particular disease. However, this high degree of designability comes at the expense of high complexity. Optimizing mRNA is a very difficult combinatorial problem, and the importance of understanding how you sequence, modify, and structure the molecule affects the stability and efficiency. And this has to do not only with the behavior of the molecule in the lab, but also in terms of manufacturability and stability in moving from the manufacturer to the consumer. So let me give you an example of what we mean by mRNA optimization. The secondary structure prediction problem that we are discussing today is part of a bigger problem that's called mRNA optimization. You start with a sequence of amino acids. So each of these letters that you see here, it's an amino acid that can be expressed via this table here to a sequence of nucleotides. And this sequence of nucleotides can fold naturally into these pairings, and that's a stable molecule. These pairings are predefined, and then not all the pairings are possible. So what is known in the in the field as a codon optimization is basically trying to find which of these three-letter nucleotides here can express each of these amino acids. So these three-letter combinations here are called codons. That's why this problem here is called codon optimization. So going from amino acid to nucleotides, this is the codon optimization problem. We are not concerned with this problem in our study here, but we're concerned with this problem, how given this sequence of nucleotides here, I can go from here to there. And how can I predict this stable structure? This is like I said, a hard combinatorial optimization problem. Classically, there have been many approaches. Of course, there is a mathematical programming approach, which is what we base our research on. There is a dynamic programming approach based on a very clever observation by Nusinov and then extended by Zucker. Basically, Nusinov's algorithm just found the maximum number of pairings, but that was not guaranteeing to have the stability of the molecule. And then Zucker introduced the energies. There are more exotic approaches to the problem, like using stochastic context-free grammars, which is a very interesting approach that attempts to solve the whole optimization problem from amino acid to folding. And of course, there is machine learning trying to find the patterns and genetic algorithms and what have you. In any of these approaches that have been going on for many decades, the success rate is about 72%, which means that we can successfully predict what happens in the lab around 72, 74% of the time. On the quant, so people thought, what if we could do something with quantum? And the approaches basically have been based on solving the problem defined classically in one of these methods here with quantum. So basically starting with a math programming approach or a Hamiltonian that you can build as a QALO, as a quadratic unconstrained binary optimization problem, you can apply quantum annealing, or there have been gate-based approaches that mostly attempt to solve, have solved the problem with simulations in a very small number of qubits on hardware. Digging a little bit deeper into the structures and what we are dealing with. So this is a sequence of an RNA molecule. You start at this point here, and you end at this point here, and the sequence goes like that. So as you can see, it can fold in many complex ways here. And they have identified different substructures that are stabilize or destabilize the molecule. So to start with, if you want this chain here to fold, you need this part, this blue part that's called the hairpin, to have a minimum length, because if it was only one, it would be physically capable of folding. So there is a minimum hairpin length involved as a constraint. And then we know that consecutive pairings are stabilizers. So you want to have long chains of pairs here. As you can see in this upper right picture here, consecutive pairs have like negative free energy, while loops, like the bulge loop you see here, the multi-loop you see here, and the internal loop you see here, as well as the hairpin, all of these are destabilizing forces. Some of them necessary, but then they reduce the stability of the molecule. Finally, you have this structure here that's called a pseudoknot, and it has been proven theoretically that if you model this structure into your problem, this makes it NP-hard. In our initial study, we ignore the loops and the pseudoknots, and we consider all the other constraints plus some non-crossing and some dangling. Dangling constraints would be like things that are falling, that are hanging over the chain here and here. As I said, we are focusing on the math programming formulation to get a quadratic unconstrained binary optimization problem. And there are basically three ways to model this problem. One is to identify your variables as pairs. So for example, you can see here in the green square, the pair is Xij. So I have taken a small snapshot here. So you have a chain that goes from sorry about that, goes from I to I plus 1, I plus 2, folds like that, and continues down here. So if I want to model this, I model xij as one variable, xi plus 1, j plus j minus 1 as another variable, etc. That's the pairing formulation. Then there is a stacks formulation that basically tells you, okay, to model these three pairings here, I say I start at I end at j, and my stack has a length 3. So this will model this whole structure here. Of course, you could say I can start at I, end at j, and my stack has a length 2, in which case you model this thing here. So all these have to be generated as variables. Finally, there's a quartet formulation that you can see here in the red box. And basically, if I wanted to model it here, I would model with these three structure, I will model with two variables. One variable would be these two pairs, and the other would be these two pairs. So basically it says I, j, I plus 1, j minus 1, this whole thing is a variable. So if this variable is 1, these pairings must be done. So basically defining my variables in any of these ways and having some energy data, and also being able to identify substructures as constraints or with penalties, I can model this and try to find the most stable structure. In our study here, we chose to go with the stack of the quartet formulation. So basically, our variables are xij, I plus 1, j minus 1, which means that if I is paired with j and I plus 1 is paired with j minus 1, this variable is 1, otherwise 0. And you can formulate this by taking a minimization. You minimize the free energy, which is this. And then you take some constraints that reward consecutive quartets and penalize some structures that are not really desirable as a dangling pairs. Also, we consider these constraints here that basically tell you that the two crossing quartets cannot be both selected. This can be also modeled on the objective function. The reason we have it here on the classical model is that classical optimizers, exact optimizers like Cplex work much better if you have these constraints here rather than the objective function. But the fact that these here are two binary variables that says not both can be one, basically can be easily modeled as I penalize the product being 1. So I want this product to be 0. So by just doing this substitution from this constraint to this constraint and keep the rest the same, I end up with this formulation here, which is a quadratic because I have quadratic terms here and there and here. Minimization, it's unconstrained. I don't have any constraints, it's binary. Now you will notice that there is a difference between the variables I use here and the variables you see here. You can think of Qi as Qk as a sequential, the sequential indexed variable of this form. That was the mapping phase of my problem. So I know how to take my problem and model it and have a Hamiltonian. The next step was to figure out on a real machine, like on a device, how to select the qubits. So what we follow the paper by McKay and all here that basically takes a layer fidelity benchmarking approach. Basically, you create layers of these joint sets of qubits. In this case, we have three layers: the blue, the red, and the green. And basically, they cover the whole all your qubits, all the neighborings. And then we apply this simple circuit here, which is a swap gate. We have a Hadamard gate here to put this in superposition into the swap, and we put another Hadamard here. and you know what the result should be. So basically, what we do is we execute this, and then we measure the fidelity of the ideal bit string that we should expect to come to receive at the end after measurement with the obtained one. And this gives you fidelity. As you can see, these numbers here is couplings, like pairs of qubits. And basically you see that they are ordered by higher to lower fidelity. So we put a threshold of 85%. So if a pairing is below 85% fidelity, we didn't consider it. This way, we create a 100 qubit chain that exclude the qubits that have low fidelity. And in this diagram here, that is one of our Eagle processors, if you see, I mean, for those familiar, you will notice, first of all, that it's rotated minus 90 degrees. But like, if you follow the paths here of the dark colored circles, which are the high fidelity ones, you will, in the colors on the links, indicate which couplings come from, the blue, the red, or the green. You will see that there is a clear a chain from 27, from qubit 27 to qubit 37 that contains 100 qubits. And that tells us which qubits to use from the device. That was the optimizing our the device for the runs that we want to make. And then what we are going to run. We chose to use the CVAR VQA, variational quantum algorithm. Basically, variational quantum algorithm is that it indicates that you have an unsudge, which is parameterized, and we start with a very simple two local unsudge here, which is shown here. This is a two local unsudge on 3 qubits. And then we repeat this you repeat this p time, so you have p layers. The entanglement is these control Z gates that you do here. And the one we chose was double linear. So basically it goes 1 to 2, 3 to 4, and so on. And then the other one goes 2 to 3, 4 to 5, etc. So this is, so in that sense, with that scheme, all the qubits are entangled. And run this circuit through the quantum computer, you get a sample distribution of samples. You calculate the expectation. Now the expectation is calculated classically. In our case, we don't use the estimator, but rather than the sampler. And in addition, we're using a CVAR approach. CVAR basically is conditional value at risk. It's a method that's being extensively used in finance, and basically says you don't want to consider the expectation of your whole distribution, but you specify a parameter, let's say alpha 10%, and you say I will consider the 10% lower end of my distribution because that's the highest quality solutions that I have. As an external optimizer, we use an FT optimizer, which is remarkably stable under noise in our experiments. The NFT optimizer has the feature that optimizes one parameter at a time. So you have pretty much control of how many iterations you run, because you can run, if your circuit has like 100 parameters, you will run 100 iterations for one epoch, and then you can specify how many epochs you want, so you have control over your over your iterations. These runs were done last year when sampler version 1 was there. Since then, this has been deprecated, but that's what we used with optimization level 3. As an error suppression mitigation, we used dynamical decoupling, and also we tried M3, which eventually we ended up not using because it gave us more overkill than value for our particular problem. And here are the characteristics of the circuits that we ran. So we ran the smaller sequences, 26, 40, and 50 qubits. We ran them on Brisbane and Osaka, which are Eagle processors, and the 80 qubit we ran an IBM Termina, which is a Heron processor. And you see the qubit, the circuit depth, and the gates. The ECR gates are native in these Eagles, and the control Z gates are native in Torino. So that was our planning for execution. And then post-processing phase is pretty simple for us. So we have a bit string that's the best bit string we found with our algorithm. We convert this bit string to this construct here that's called the dot bracket. If you notice, the dimension of this is not the same with that. This is the dimension in the dimension of the number of variables that we have, the quartets that we created, and these correspond to each nucleotide. So basically, this dot tells me that the nucleotide is not paired. So this C, you see the first nucleotide C here is not paired, but the second one is paired. And there is a unique way to go from here to this, and we're using the Forna server, which is a web service that Vienna RNA in the University of Vienna in Austria provides, and then you can provide this input and you generate the graphic so you can see how the folding works. So that's the whole setup that we have. We map the power problem to a Hamiltonian. We optimize our circuit. We define how we're going to execute and how we're going to process our results. And then let me talk about some results here. So classically, we solved this with simplex. We generated 10,000 sequences of lengths 15 to 60 nucleotides. Simplex had no problem solving those, but you can see that the time it took to solve those started increasing exponentially. And even though our model didn't include all the structures, it achieved like 64% accuracy in the solution. So basically, it solved 64% of the solutions to optimality, to the optimal solution known from the classical software they use in biology. Then we ran our results on simulator. We ran our experiments on simulator, and here are the results. So what we did, we took sequences of 10, 15, up to 40 qubits, and we ran each of these 10 times. And for each of these 10 runs, we found the optimal solution in at least one time. And this chart here shows you the probability of success. So when you had 10 qubits, we were always finding the optimal, and we were pretty good at 15, 20 qubits, and then we started getting lower success probabilities, although sometimes we get pretty high mean values. What are some observations from running on a simulator? And when I say simulator here, we use the matrix product state simulator, MPS. So first, the whole scheme is very sensitive to alpha value, which is the parameter of the CVAR. The second is that increasing the P layers gives you better results in the simulator, but as we will discuss, as you can imagine, in the hardware, that increases the depth, so the performance deteriorates. Then that's common for like all variational schemes. The last 2 points, it's the starting point sensitive, and they have large flat areas in the landscape. So this is something that can give you to barren plateaus and be stuck in a local optimal that you cannot escape. And this is also a mechanism to escape this optimum, because if you start from a better point, you will not get trapped there. This has been observed by other researchers too, that the particular formulations have these flat areas. So this was encouraging, like at least we hit the optimal solution sometimes. So we decided to run this on hardware. And this slide here is split into two. With the left side is the runs on the Eagle processor for 26, 14, 50 qubit problems, which correspond to 25, 30, and 30 nucleotides. These were on the Eagle processor of Brisbane or Osaka, with one layer in the ansatz and 0 to 5 as an alpha. And we used the optimal solution in all three on hardware, with a probability of success, if you draw this line, about 40%. And here it tells you how many times you run. We ran 8 trials here, 14 here, and 15 there. And the number of shots of each experiment was there. That was good, so we moved to solve a bigger problem. Due to runtime limitations, so we decided to do the training offline. What does this mean? We set our alpha to 0.1 and we use two layers. Then we run the simulator to obtain the optimal theta values, the optimal parameter values. And then using the optimal parameter values, we started one iteration on the Heron processor on IBM Torino. And we're able to to get the solution for the 80 qubit sequence, which corresponds to 42 nucleotide length. As you can see from this picture here, we not only we found the optimal solution, but we sampled it with the highest probability of the other solution. So that was really a good experiment. And these are different solutions that we obtained for the 42 nucleotide sequence. And one thing I want to point out here is you see how different your configurations can be in these three here. You have almost the same energy, and how you can see how different the pairings are. So this indicates the problem with the flat areas that I was talking about. Also, you can see how even if you are not optimal, a close to optimal solution is very close to the real optimal solution in terms of folding. So to summarize, since I'm almost out of time, we set out to examine the feasibility of attacking this problem with a quantum computer, and where we found that we can get useful results with minimum mitigation and suppression on real hardware for much larger nucleotide sequences that have ever been tried. Now, in an upcoming paper that should be out this month or the next, we will show results that we exceeded like 100 plus qubit runs. We reached the maximum 156 qubits on the Marrakesh, and that corresponds to 60 plus nucleotide sequences. And also we examined ways to reduce the qubit requirement. So basically make a tighter formulation. Observing our solutions, we found that our solutions have very low Hamming weight, so that indicates like a redundancy. This doesn't, sorry, I lost my, so this doesn't have to be quantum. This tightening of the formulation can be on the classical side. Also, our research indicates that we have to use more complex answers and that get more deeper circuits, but they give us better sampling, and also the optimization techniques, the available optimizers, external optimizers for the variational scheme need to be more efficient than what we have right now. So this is an open area of research. And I believe that's all I have to say. Any questions?
There is no question inside. Thank you very much. The session is over.
Thank you.
모든 세션이 끝났습니다. 지금부터 휴식 후 오후 1시 30분부터 두 번째 세션을 진행하겠습니다. 모두 참석해 주셔서 감사합니다. After a short break, we will proceed with the second session at 1:30 p.m. Thank you for your participation. 잠시 안내 말씀드리겠습니다. 지금부터 연세 퀀텀위크 2025 인더스트리 세션 두 번째 세션을 시작하겠습니다. 두 번째 세션은 D-Wave의 스위치 후쿠다님께서 Quantum Optimization for Mobile Network Performance라는 주제로 온라인 발표를 해주시겠습니다. May I have your attention, please? We will now begin the second session of the Yonsei Quantum Week 2025 Quantum Industry Session. In this session, Shuichi Fukuda from D-Wave will give an online presentation on the topic Quantum Optimization for Mobile Network Performance. Please welcome.
네, 안녕하세요. 저는 슈이치 후다입니다. I'm from NTT Docomo. I'm very happy to here to present a case study on quantum computing at Yonsei University. NTT Docomo is a mobile operator in Japan, and we are working with KT and SKT and exchanging ideas and opinion on telecom technologies. In recent years, with the advantage of generative AI, the development speed of IT services has become very fast, and the field of quantum optimization can't be no exception. I strongly believe that the telecom operator can provide the various fields, various domains based on the customer data with their field. And by processing large number of data, we can optimize the use of the data. What I want to say is that company with the wide various of data have the potential to make a good plan and realize many optimization ideas. Today, we will present a case study of quantum optimization in telecom field at NTT Docomo. So, okay. Can you see my slide? Yes. Okay. Let's start. The title is Developing a Quantum Computing Platform to Optimize the Services. First, this is a mechanism for determining cell phone coverage areas. Mobile operators set up the base station throughout the country to connect terminal everywhere, and each area divided and covered. This is a terminal, and this is a base station. The terminal registers the location when it's moved across an area named TL list, and a different TL list number assigned to each area. The location registration area is divided to narrow. Many location registration process will occur. It leads to a large load on the network. So NTT Docomo developed the efficiency division method, the optimization. This is the overview of tracking area optimization. When a terminal receives an incoming call after moving within TL list, the terminal can determine its current location by sending a paging signal to a group of base stations. So it's called TA list, TA, which is a smaller area than TA list. Left figure is an example of paging signal to grasp current terminal locations. First, current central unit send a paging signal to last connected base station. And terminal response it, the central unit can resolve the current location. But the terminal moved, but terminal moved, central unit has to send the paging signal to tracking areas. So that in right figure shows the concept of TA optimization. The illustration shows the TA groups divided with terminal moves in base station network. The arrows means the amount of terminal moves. Oh, by the way, how tracking area is determined in general? For example, in manually, one common method of determining the TA is to look at the map and determine the human eyes that maps road and highway and railroads will be in same TAs. So let's try to set the TA to optimize the number of paging signal by using two TAs. You can find the main flow with the red line, and also you can see the city area in orange areas. Identify major road and the urban area on the map. The general setup procedure is listed in left and right. First step identifies the major road and urban area on the map. The next step is to divide the area considering with located major traffic lines in same TA. And final step, assign to the same TA code to base station belonging with the TA area. I designed TA pattern with A. How is this? Main flow and most cities are placed in same TA, and it seems good, but this is the next pattern B. The main flow across the TA border twice, but if the population in the blue area is large, the overall amount of paging signal will be less because its paging transmission area is smaller. So it is not possible to accurately determine the number of paging signal. So the map can take into account the flow of people on Main Street, but it is difficult to take roads, but the branch off from each others. The map cannot capture the area where the terminal movement is complex, such as underground area around the station and buildings. This is the flow of TA optimization. Our TA optimization uses the formula to estimate the paging signals based on the device movement device movement data between base stations. The data is converted from the device control log. We also develop a map visualization tools to display the TA allocations and optimization results. Finally, the estimated reduction in paging signal is submitted to the branch office of our network. Since TA optimization is performed only one few times in a year, there is no need for real-time optimization, but the number of combinations increases with the number of base stations and TAs. So a single solve can take a numerous amount of time. Once the TA optimization is done, the operator staff at the branch office will review the optimization result and make correction. Therefore, the time required for each solve should be short. Classical computers struggle to solve the large combinational optimization problem with the time increase exponential with the problem scale. For example, quantum annealing can find a good solution to those problems in a fixed time. This is an example of the TA program. It takes so long time. Also we developed a tool to visualize TA allocation. Each point presents a base station. This one is the base station, and the color is TA. The line means the amount of movement. This visualization tool helps to ensure the TA groups is for measure load. This is maybe this is a CT, and this is a tonal thing. And yes, this is a result of trial in actual network. We tested our quantum annealing results in actual network. The result shows 15% of reduction in paging signal. It's improving network efficiency and communication quality. The graph highlights the decrease in both maximum and average paging signal after the trial started. We have developed a quantum computing platform to optimize the various aspects of services. The platform integrates for high precision and low cost efficiency optimization calculation. It connects to our customer data with quantum computing platform. It allows us to leverage quantum annealing. The hybrid approach enables us to track complex optimization problems with various scales and accuracy requirements. We believe that our quantum computing platform has the potential to realize various fields, not just telecommunication. Beyond our own industry, we see potential in areas like construction, where it could optimize equipment and potential planning. And we also expected about the future of quantum computing and its potential to drive innovation across industry. That's all. Thank you for listening.
Hi, Fukuda-san. This is Jeremy. Oh, is he still there? Ah, okay. Is there anything you can talk about the future innovation areas on the last slide that you were showing?
We are focused on first. We are focused on the telecom field. Oh, sorry. You see earlier, and maybe next is finance, because I'm belonging to finance earlier. So I want to try to optimize the portfolio optimization and other problem maybe.
Okay, thank you.
Yes, thank you for your question.
One,
Yeah, okay.
if one more question. Can you talk about what the process was for optimizing the TA list before implementing D-Wave? You talked about the map method. Was that the main method, or did you have some other, maybe an algorithm that ran on classical computers using a small number of TA areas, or were you? Was it completely manual?
The first time in NTT Docomo, the branch office using the map, and they determine the TA area. But next step, we use the algorithm to determine the area. It is not using the quantum computing, but the problem was the algorithm can't solve the TA problem because it uses classical computers. So in our approach, we use the quantum computing, and it makes a good result with high efficiency and less time. Yes.
Okay, so you tried previously, before implementing the quantum solution, you tried a classical solution, but it was unable to give you good results due to the large problem size. Okay, understood. Thank you.
Yes.
Someone asked a question on YouTube. Thank you for your talk. In your case, you applied 270 base station. Are you going to increase more base stations? And second question is, what's your next plan?
Okay, thank you for questions. This is an example of the TA problem. The number of base station and TA becoming bit larger. So the problem is becoming very large problem. So we have to use the quantum annealing. And second question, next step is Next step is we are trying how can I say, we're trying to determine the TA. The next step is, I think, TA list. The problem is not TA, not increasing TA whole TA list. It become a more larger problem. So we have to make please wait. We have to develop this middle software, and you have to make a Hamiltonian for optimization. It means a formula of how can I say? It's formula to minimize the pacing and other network indexes. Yes, that's all.
Once again, a big thank to you for the insightful presentation. With that, we conclude this session. Thank you very much.
잠시 휴식 후 2시 30분부터 세 번째 세션을 진행하겠습니다. 잠시 후에 뵙겠습니다. 감사합니다. After a short break, we will proceed with the third session at 2:30 p.m. See you shortly. Thank you. 잠시 안내 말씀드리겠습니다. 잠시 후 2시 30분부터 연세 퀀텀위크 2025 인더스트리 세션이 진행될 예정이오니 아직 착석하지 않은 참석자분들께서는 자리에 착석해 주시기 바랍니다. May I have your attention, please? The Yonsei Quantum Week 2025 Quantum Industry Session will begin shortly at 2:30 p.m. If you have not taken your seat, please do so now. 잠시 안내 말씀드리겠습니다. 지금부터 인더스트리 세션 세 번째 세션을 시작하겠습니다. 세 번째 세션에서는 D-Wave의 정성근 님께서 Quantum Advantage for Logistic Optimization, Quantum Solution for Operation of the Busan Port Terminal 이라는 주제로 발표해 주시겠습니다. May I have your attention, please? We will now begin the third session of the Quantum Industry session. In this session, Mr. Seon-Geun Jeong from D-Wave will give a presentation on the topic Quantum Advantage for Logistic Optimization, Quantum Solution for Operation of the Busan Port Terminal. Please welcome. 큰 박수 부탁드립니다.
Hello, I'm Seon-Geun Jeong, and I'm a PhD program student at Busan National University. In this quantum industry session, I would like to introduce our quantum advantage project because I think the quantum industry session is to introduce the quantum computing can be used in industrial, and so I think our quantum advantage project is suitable. The topic is quantum advantage for logistic optimization at the Busan port. In this project, our consortium consists of Busan National University, KAIST, Komeri, Busan Port Terminal, and Busan Metropolitan City. First over, I would like to the quantum advantage project, so we can know what is the quantum advantage project and what will we do. And after that, I will show you the research process and research result and our future work. In the field of logistic optimization, material science, cryptography, drug research, and financial optimization, it is difficult to solve these problems using classical computer, but quantum computing is known as a promising technique to solve these problems. So the Ministry of Science and ICT wanted to verify the potential of the quantum computing in industrial. So from up to now, maybe 6 projects are adopted. Our project is one of the projects in this quantum advantage. Okay, I will introduce our research background and necessity. South Korea is the highest trade dependency globally. With respect to the trade dependency in Growth 20, Korea is third in export and second in import. In addition, 99% of international trade is handled via maritime transport due to Korea's geographical characteristic. And Busan Port is the largest maritime trade gateway in world. Busan Port ranks second in transshipment and 7th in total cargo volume. And Busan Port handles 75% of South Korea's cargo volume, so Busan Port is very important in Korea. However, the Busan Port's global port competitiveness decreases every year because in Busan Port, they make a plan based on their experience. So they don't use any algorithms. So sometimes it is inefficient and they cannot respond to the unexpected events. And the IMO, International Maritime Organization, mandates carbon emission reduction of ships. So it is important to make a plan optimally. And let's see the right side figure. And there are a lot of terminals in the world. Specifically, in Singapore, the government manages their terminal. So they use the same terminology, and they use the same process, and they use the same data format. But in the case of the Korea, we in Korea, private terminal company manages each terminal. So each terminal uses different terminology and different data format, and they have different operating process. In addition, in Korea, the ships usually come from Japan and China. So maybe it takes 3 hours or 6 hours. So it is important to respond quickly. This means lack of standardization, and these issues lead to decline the logistic competitiveness of Busan Port. So our quantum advantage project goal is to optimize port logistics using quantum computing technology by achieving quantum advantage and enhancing Busan Port's global competitiveness. At the Busan Port, the port planning manager establishes this berth allocation 3 days in advance. But frequently, this scheduling should be rescheduled because sometimes the ship can be delayed due to the weather or previous port working delay. And the key crane can be breakdown. For example, the sensor of key crane or operating system of key cranes can be breakdown frequently. At that time, we cannot use these berths. So the rescheduling is required, and the key crane worker is human. So working time depends on their experience. So sometimes working delay is occurred, and this timetable is made by humans. So sometimes ship overlapped and unused berths are also occurred. In this case, rescheduling is required, but it is difficult to reschedule quickly due to the high complexity. In addition, the IMO mandates to reduce of greenhouse gas emission of ships. According to the report of Carbon Global Industry Alliance, optimizing the ship speed between previous ports to arrive just in time can reduce greenhouse gas emissions by 10%. Let's see below figures. This is a timetable, and we provide this timetable to the ship company, and the ship company will come to Busan port at this time. So the ship will come at the previous port with full speed, but this is not optimal. So they will wait at the port. This is port mooring time. At that time, the greenhouse gas will be occurred. But if we optimize this berth allocation plan, or if we respond quickly to the unexpected event, then they can manage their speed. This is just in time. In this case, the ship company can reduce their greenhouse gas emission. Okay, I will show you our research process. In this page, I can summarize our quantum advantage project. In general, at the port, it is divided into two sides. One is key side, and the other is the other side. In the key side, the ship comes and they wait and they dock to the berths. After that, the key cranes are assigned to the vessel, and the key crane load and unload the containers, and the containers can be moved on the storage in yard. Our quantum advantage project focus on this key side. Specifically, in the key side, the terminal company allocate the vessel to the berth. This is berth allocation, and the terminal company assigned certain number of key cranes to the vessel. This is key crane allocation. After that, the containers load and unload order is determined. This is a key crane scheduling. But after that, the yard operation and gate operation are conducted. In our project, we focus on these problems. In the case of the first allocation problem, let's see this figure. The sky blue rectangular is ship. The y-axis is length of ship, and the x-axis is processing time for loading and unloading containers. And this orange is the first section, and this x-axis is time. So we assign the ship to the first while considering the time. This is the result. And after that, we assign the key cranes to the vessel while considering the moving range of key cranes to satisfy the processing time. To solve this problem, we proposed quantum computing framework. First of all, we received the Busan port terminal port data, and we formulate the berth allocation problem and key crane allocation problem. Actually, this problem can be solved using classical computer, but to solve this problem using quantum computer, we should convert this problem into the QALO model. So after formulation of QALO model, we apply pre-processing to reduce the searching space, the cost, and after that, we apply D-Wave CQM solver, and we can obtain the solution, and we apply the post-processing algorithm. It can improve the solution, and it can make this timetable. From this timetable, the port planning manager refer our result to make their berth planning. In our quantum advantage project, there is an important issue. It is securing D-Wave quantum computing resources. To secure the D-Wave quantum computing resources, we visited D-Wave headquarters and we presented our quantum advantage. And after that, we frequently had a Zoom meeting, and after that, D-Wave visited the Busan port terminal, and after that, finally, we successfully signed to the contract to use D-Wave quantum computing resources. And we studied with D-Wave collaboratively, and we obtained good results, so we can present at this time, and also we will present Qubit 2025 conference. And this is one of the another issue. Our major is not port logistics, so we should learn the port logistics, and quantum advantage project consider real problem size. So we received real port data from BPT, and we learned the real port logistic process in BPT. So we defined the berth allocation problem and key crane allocation problem based on BPT. And we also visited the test bed, and from this our defined berth allocation problem and key crane allocation problem, and we studied. Okay, I will show you our research result. First of all, I will show you the IBM Quantum computing based berth allocation. In this case, we applied the QALO algorithm. This is Covilla optimizer based result. This is just iteration. Finally, our result is that QALO can solve a berth allocation problem for 3 ships, but in real problem size, the port planning manager consider weekly plan. In weekly plan, they consider 50 ships, so it is not enough. So we used the D-Wave quantum computing based burst allocation. In this burst allocation, we used our proposed hybrid quantum computing, and we obtained this burst allocation problem with 3 shifts, and we adopted benchmarks as such as branch and bound, genetic algorithm. Genetic algorithm and branch and bound are widely used in this field, and CQM solver is D-Wave solver, and our algorithm also include D-Wave solvers. And CQM solver and our algorithm can solve this problem within 30 minutes. Specifically, the burst allocation problem and key-crane allocation problem should be solved within 1 hour. This is required real time in the real field. But the genetic algorithm and branch and bound algorithm cannot satisfy this real time. In the case of the key-crane allocation problem, we also used this algorithm, and our algorithm can obtain the suboptimal within 2% error. In terms of the computation time, the D-Wave CQM solver and our algorithm can satisfy the required real time. So from these results, we verify the potential of D-Wave quantum computing based logistic optimization. Okay, I will show you our future plan. Actually, our quantum advantage project began from last year. So the phase 1 is completed. In the phase 1, our goal was, in the case of the burst allocation problem, we wanted to solve the 23 shifts, 5 vertices within 1 hour. In the case of the key-crane allocation problem, our goal was to solve 15 key-cranes, 5 shifts within 12 hours. But we obtained this result in the case of the burst allocation problem. Our result is 30 shifts within 1 hour. In the case of the key-crane allocation problem, we solved the 15 key-cranes and 29 shifts within 1 hour. So in phase 1, we verified the potential of the D-Wave quantum computing based solution, and from this year we begin phase 2. In this phase 2, we will improve the problems. We increase our problem size to real problem size. In real problem size the problem size is 50 ships, 15 key cranes, and 5 vertices. So we should solve the problem from 30 ships to 50 ships. And I aforementioned before, the rescheduling is required frequently. So in that case, the rolling horizon algorithm is required. So we will implement the rolling horizon algorithm from this year. Specifically, the rolling horizon algorithm considers just a certain time window. So, for example, for 3 days, the scheduling is conducted again and again and again. But in the case of the phase 1, we just consider weekly plan. And in the case of the standardization, the BPT and Busan Port Authority and Komeri consider this one. BPA announced the chain portal. In the case of the chain portal, we can share the logistic company, ships company, terminal company, driver company's information can be shared simultaneously in real time. From this platform, we can receive the port data, and we can use this quantum computing framework. And this standardization is important because in this quantum advantage project, we consider only the BPT, but when we consider another terminal, at that time the data format or the operating process should be standardized. And when we consider the outside, then this, if another port and another terminal use our standardization, then they can use our quantum computing framework. Okay, thank you. Is there any question?
Once again, thank you for your wonderful presentation.
Thanks for the talk. Do you have any plans or any thoughts about, I'm sure there are similar problems in other ports. Do you have any thoughts about doing similar work at other ports, or have you considered, looking at data from other ports?
Actually, in case of the Busan port, there are several terminals. For example, Busan port terminal or Hanjin terminal. In that case, Busan port terminal used the vessel name like based on IMO standardization, but another company used another vessel name, even it is same vessel. So in that case, the data format should be standardized, and after that, our quantum computing framework, we formulated the optimization problem. In that case, we require certain variables, and in that case, if we consider expand or other things, they should share our required variables. All of these things should be standardized. After that, we can apply anywhere.
Okay, I see. So standardization of the input data is one of the biggest challenges in terms of putting it, implementing it at other terminals and other ports.
Yes.
Okay, thank you.
I think it would be important to feedback some schedules by using some real data, because there will be some variation of scheduling. So do you have any plan for those kind of feedbacks in real time?
Actually, in BPT, they first determine the Bursal location, and after that, they determine key cranial location problem. In this case, we can support our quantum computing-based result to them, but in this case, we cannot include all the real constraints, or in addition, there is a relation between terminal companies and ship company. Sometimes this ship should be assigned in this section in this time, but we cannot include in our algorithm, but based on our result, they can refer the assigned shifts. At the time, maybe the port planning manager refer our system, but in real system, they requires the result should be obtained within 1 hour. So within 1 hour, if we support the quantum computing based result to them, maybe they can use our result to make their plan.
Thank you very much.
We truly appreciate your time and expertise. Thank you very much.
잠시 휴식 후 오후 3시 30분부터 세 번째 세션을 진행하겠습니다. 잠시 후에 뵙겠습니다. 감사합니다. After a short break, we will proceed with the third session at 3:30 p.m. See you shortly. Thank you. 잠시 안내 말씀드리겠습니다. 잠시 후 3시 30분부터 연세 퀀텀잉크 2025 인더스트리 세션이 진행될 예정이오니 아직 착석하지 않은 참석자분들께서는 자리에 착석해 주시기 바랍니다. May I have your attention, please? The Yonsei Quantum Week 2025 Quantum Industry Session will begin shortly at 3:30 p.m. If you have not yet taken your seat, please do so now. Thank you. 잠시 안내 말씀드리겠습니다. 지금부터 오늘의 인더스트리 세션 마지막 세션인 네 번째 세션을 시작하겠습니다. 마지막 세션은 영국 포츠머스 대학교의 주재우 교수님께서 Quantum Simulation for Dynamical Transition Rates in Open Quantum Systems 라는 주제로 발표해 주시겠습니다. May I have your attention, please? We will now begin the fourth and the final session of the Quantum Industry Session. In this session, Professor Jaewoo from University Portsmouth will give you a presentation on the topic Quantum Simulation for Dynamical Transition Rates in Open Quantum Systems. Thank you.
Good afternoon, everyone. My name is Jaewoo from the School of Mathematics and Physics at the University of Portsmouth in the UK. And I'd like to thank for the organizer to give me these opportunities for this wonderful conference, Yonsei Quantum Week 2025. And the title of my talk is Quantum Simulation for Dynamical Transition Rates in the Open Quantum Systems. So I hope everyone kind of agree with, now we are in the noisy intermediate scale quantum computer, and we are aiming to achieve fault-tolerant quantum computing in the future, possibly in the cloud platform, for example. And in my research, what I like to achieve are the, academically, it's like quantum computing for chemistry and also the cosmologies. And in the industry viewpoint, we hope to have some improvement in the finance and the quantum AI in the future. Today, I'd like to focus on a little bit on the quantum chemistry or quantum physics side, but I suppose it can be linked to the industry researches in the future. So my talk starts from the quantum computing foundation fundamentals at the beginning, and then I'd like to move on to the quantum algorithm and on the physical quantum computer. And then I'd like to move on to the next two topics. And first topic is about the quantum algorithm for the master equation solver. And for example, we can investigate the steady state quantum solver under the Lindblad evolutions. And this is a kind of main topics for the mixed state quantum simulation for the Markovian quantum systems. And this is directly linked to the title of my talk. And then I'd like to wrap it up with a question and answer at the end. So one of the main questions in my mind is what can a quantum computer do? And you probably have your own answer for this one. Then when I give a talk for the previous years, I started from the superposition and entanglement, and sometimes the audience got confused, and also I had a little bit difficult to explain what is a superposition and entanglement. So my definition for the quantum computer is recently was about the linear algebra computer. So if you would like to look at these things, I'd like to go back to the technology revolutions, for example. And in the 18th century, 19th century, we had the analog technology revolutions. So I suppose you probably have these LP players, or you have seen at least the LP players, and this is based on the classical or thermodynamics. So it had pretty much well developed in the early years. And then afterwards, in the middle of the 20th century, we had the digital technology revolutions, actually based on the electromagnetism. So in the physics viewpoint, this is the quite rapid revolutions in a sense. So if you look at this one, this is one of the early portable computer in the early 80s. And this is really good for engineers because they can do works wherever you want. And also this was good for the health because it's about 13 kilograms and then you need to carry on everywhere. So this was a really good kind of ideas to carry on 13 kilogram of the personal portable computer. And in the 21st century, we are thinking about to use quantum dynamics for the technology revolution. And the key question would be what is the difference between digital technologies and quantum technologies? So I have a kind of examples to think about it as a matrix multiplications. So if we have a matrix A as a 4x4 matrix, and it's applied onto the 4x1 column vector, vector C. And what we are doing in the classical computer is we take the value A11 and then multiplied with C1 and putting into the memory. And the next step would be take the A21 multiplied with a C2 and putting into the memory. Then if you're doing again and again and with the addition, we will end up with a 4x1 column vector with multiplications and summation. So that's 1x1 calculations in the classical computing. However, if we are using a quantum computer, we actually have this vector C with the physical systems, and then we can apply 4x4 matrix. For example, if this is a superconducting qubit, we are applying microwaves onto the 2 qubits. I didn't say yet what is the definition of the qubits yet, but and then it makes like a simultaneous kind of computing, in a sense, for the matrix multiplication, for example. So if you accept this kind of linear algebra, and you can easily understand superpositions, and if we are using a classical computer, we are using scalar values, but in a quantum computer, we are using a vector, especially 2x1 column vector is the information unit. So you can think about quantum coin spinning, if you can think of it, and you can think about state 0 as in the UK, although we have a king now, but we still have a queen on the coins. So if queen is on the top, then it's a state 0, and if queen is on the bottom, we have a state 1. And then we can make a representation of the 2x1 column vectors for the state 0 and state 1, as you can see here. However, if you accept this linear algebra computer, then we can think about plus states as like a combination of the state 0 and 1, and which is actually queen on the left side of the coin. And minus states is another state, have like a mixture of the state 0 and 1, but queen on the right side, for example. So this is something quite different information units if you think about only state 0 and bit 0 and 1 in the classical sense. And if you have more than 2 quantum coins, you can make the entangled states, and that is like state 0 on the left side, state 0 on the right side, and also state on the left side is 1 state, and then 1 state on the right side and left side. So let me give you a brief ideas what is the correlation, quantum correlation states. It's equivalent, nearly same as entangled states, for example. So if you can think about state 0 on the left side and state 0 on the right side, plus states on 1 on the left side, state 1 on the right side, and that is we call the pi plus state, for example. And now we can think about quantum coin spinning. And if we have 1 coin, we can measure these coins horizontally. Then we end up with a queen on the top as a state 0, as I defined, and queen on the bottom is a state 1. However, we have another way to measure in the vertical ways, and as I said, this could be a plus state and minus states. And if we have this plus and minus state, and we can also measure horizontally, then this plus state should be given as a 0 state and 1 state, and let's suppose we put a plus state in the middle. Then for the minus state, if you measure horizontally, then it ends up with a 0 and 1 states, but we need to distinguish these plus and minus states. So one of the ways is just put a minus sign between the 0 and 1 state. So this is like you're accepting these quantum coins, which is different from the classical coins. And then we can now think about 2 coin states, which is represented by pi plus state, as you described it in the above. Then these states are designed to have a correlation. So one correlation is if you measure these pi plus states in the horizontal ways, if left coin is a state 0, and the right side of the coin always stays 0. And also, if left coin is a state 1, right side of the coin is always 1. So that can be actually made possibly in the classical correlations as well. So for example, if you have a red ball, you send it to the left side, right side persons, and then they get the same colors, and like a red ball, blue ball, for example. However, if you accept this kind of a pi plus states, we can make a little bit of a mathematics that 0, 0 plus 1, 1 state actually the same as the plus minus states, which implies this pi plus states, two quantum coin states, can have another correlations. So if we measure the left coin in the plus basis, and then right side of the coin is always plus state. And the same way, if left coin became like a minus state, and the right side of the coin became like a minus state. So if you think about to manage this kind of all type of correlations, it's impossible in the classical correlation, in a sense. So that's a kind of a naive kind of thinking that this pi plus state is beyond the classically correlated state. So we are using superposition and entanglement as a resource for the quantum computing. So let's move on to the little bit of algorithm recap. And this is my favorite definition for the classical algorithm. So an algorithm is a finite sequence of well-defined computer implementable instructions. Because if I put a quantum in two places, and it became like a quantum algorithm definitions. So in a quantum algorithm, we have quantum states as a qubit, quantum bits. And then if it is like a superconducting qubit, for example, and we need to have initialization of the state. So let's assume we have all states are 0. So that's the initialization. Then we are preparing the states as a pi lambda bar state. So lambda bar is, you can think about as a variational parameter, for example. And then how to make it is shining microwaves on the superconducting qubits with omega 1, omega 2, with the different frequencies. Then we create the prepared states as a psi, capital psi lambda bar state. Then afterwards, we are performing quantum processing, and then we are applying a beta bar operation, and then we are shining more microwaves, for example, and then we create a state like a pi with a lambda bar and beta bar. But this beta bar may be a fixed kind of parameters, and this is depending on the different quantum algorithm, for example. And the last part would be measurement. And in a quantum computing, we never get this psi state or pi state directly, because that's a wave function. So what we get is a probability of some outcomes. So we need to be smart enough to extract the quantum informations when we are having a quantum algorithm, for example. So if you are measuring all the qubits with the many qubits, it's a little bit of a pointless, for example, because it's exponential. It makes an exponential cost. So that's a kind of rough ideas about the quantum algorithms. And as you know, this is like IBM Quantum Computer Roadmaps. We are in the nearly like a flamingo stage, and people are working on to make the many qubit states. But I'd like to point out, this is like a networked QPU. So you need to design smart enough again and to think about these quantum architectures underneath. So that's one of the rough overview for the quantum algorithm. In my research, I actually using a lot of computing expectation values for the large metrics, for example. And I'd like to give you some examples what is the meaning. And if you think about this finite difference method in the first quantized unlocked state psi x. And psi x is a kind of a representation for the function, for example. Then, as I mentioned, if we have a 1 qubit, we have capabilities to write down 2 values of the function, for example. And if we have 2 qubits, now we have a 4x1 column vector, then we can store roughly 4 points of the function values, for example. And so on. If you think about L qubits, actually you can encode 2 to the L function values in L qubits. So this became like a 2 to the L by 1 column vector, so which is looks like this one. So I'm just thinking about the function values between the x from the 0 to 1, and then this became like a position vector, and S1 is the most significant bits, and the SL is like the least significant bits, and this represents positions in between 0 and 1, and the coefficient contains the information about the function. So in this sense, you can think about 100 qubits if you can use it. That is about 2 to the 100, and that is roughly 10 to the 30 function values you can encode in the 100 qubits. So this is like exponential compressed encoded information you can think about. But as I said, you need to be careful whether you'd like to measure all these 100 qubits, or you need to find the smart ways to measure and then extract the information. So this is a kind of examples that I was working on. So if you think about the variational parameter lambda, that determines the shape of the function, for example, and then we have unlocked states, and we put into the quantum processor. So let's assume we have a quantum processor 1 that is calculating kinetic energies, and at the end we get the value ET. And the second one, quantum processor, is calculating something else, energies, for example, and then we get the energy of the others. And if we adding together, we assume that is a total energy, for example, then what the shape of the inside of the quantum processor looks like this, as one of the example. So we have a control qubit, and we have input states as a function, and then we perform the controlled gate. This is a H, for example, for the Hamiltonian. Then when I measure only single qubits, we will get the probability of having 0 or 1, and this will give us the energy of the this one. And this is more likely calculating cost functions in general sense. So once we are calculating the energy, and then we have like a total energy, for example, and then what we need is like a classical computing, then make optimizing this like variational parameters to make the minimum value of this total energies. So this is one way called variational quantum algorithms to get the ground state energy, for example. However, as you know, in the quantum computer, we have errors, so we need to find a way to make error-tolerant qubit controls. For example, using error correcting code or the fault-tolerant ways, also the controllability of optimal control of the qubits, for example. So this is the one of the way to use the expectation value calculations in quantum computing. And if we now go for the little bit beyond of the closed quantum dynamics, we can think about commutator simulation. So for the closed quantum systems and also open quantum systems. So I suppose you know about the Schrödinger equations, and there is the equivalent equations called the von Neumann's equations. And they are more or less identical. And the difference is we are using wave functions for the Schrödinger equation, and we are using density matrix for the von Neumann equations. And there is a commutator in the von Neumann case. But if you think about a more generalized case, we are in the open quantum systems, and it has time irreversibilities, and which implies we have primary quantum systems that we are interested in, but there are the environmental systems that has an interaction with core quantum systems. So as you can see in this reference, and this is the kind of quantum states are coupled with other environments. So we can think about this is a more generalized case than the closed quantum systems. So in order to handle these open quantum systems, we are using Lindeblad, for example, equations, which is one of the basic equations for the open quantum systems. And if you look at the von Neumann equations, there is the first term from the von Neumann equation, which is a unitary evolutions. And also there are some extra terms that is given by Lindeblad operators, for example. So what we can do with it? So if we'd like to make a kind of a circuit quantum simulators for the commutation relations. So this is one of the examples that I'd like to talk about, and we can find a quantum algorithm for finding steady-state solutions for the Lindeblad equation, for example. So this is the Lindeblad equations. I put expectation value forms, and you can see there is a density matrix rho t inside of the expectation value form. And if this one gives the 0, which implies this rho t does not change in time, which is a steady-state solution. So what we'd like to do is actually calculating this right side of the equations by quantum computer. And then if we get this, adding all these expectation values, if it gives a 0, then we found steady-state solutions. And this one could be useful for the master equation quantum simulator with the density matrix for more generalized purpose. And the quantum circuit looks like this. So as I mentioned, we are using control qubits, and we only measure control qubits at the end. But in the middle, there is system qubits, and like L qubits, and there is a reference qubits underneath. And we start from the preparation stage, and then we are doing quantum processing, and at the end, we are measuring only single qubits. So when I measure single qubit in the control qubits, it provides us a probability of having 0 and minus probability of having 1. That is the expectation value of this function. However, if you're doing a little bit of mathematics, this will be write down in this way. So pi state was a reference state, and then z hat chi underneath A is a kind of a 2 to the L by 2 to the L matrix, which is given by this underneath like formula. And pi state is a 2 to the L by 1 column vector state. So this is actually a large density matrix calculations, but we are obtaining this one by the statistics of a single qubit state. Then, as a simple example, if there are controlled gate as controlled N, controlled A, and controlled M, and if we define as a simplest case, we can get actually anti-commutator or commutator forms as expectation values. Then, depending on the phase on the control qubits, we can change the plus minus sign between. So that's like building blocks for the second steps. So now this is about the main topics for the dynamical transition rate in the open quantum systems. So let's suppose that this is like a cartoonic illustrations you can think of. So let's assume in classical sense that we have a double well, and then I recall this left side of the well as A, and on the right side of the well is about B. And at the beginning, all the particles are on the left side. And because it has energies, like temperatures, it can have a chance to hop from the A to B, and this is the case. So it can go from the, because everything was in A, and there is a chance to go to the B, that's called the rare events. And then if there are some particles on the B side, there is also the chance to go back, return to the well A. And in this case, because there are many particles on the left side, it's still going to the right side of the well, but there is a chance to go back. So this is called the linear response domain in the transition rate theory. And then at the end, it became like equilibrium states, and it doesn't need to be all equal, but depending on the geometry of the potential, it ends up with some expectation value of the particles are static, but we still can think about there is the particles and hopping and left and right side. So, but that's like an idea of the equilibrium. So we can describe these phenomena using the correlation function, CT. So as you can see here, there was no particle in the B and at the time 0, and then it increased, and then there is a linear forms. So in time, there is a linear constant, KAB, that is actually representing the transition rate. So this is the case, and in order to get the pretty much accurate KAB, what we can do is we differentiate C, and then we have a C dot T that has like a plateau and the response, a linear response region. And that's what we'd like to compute on a quantum computer. So let's go for the quantum case. So we are kind of interested in the short period of the time evolutions, but this KAB actually determine even longer time evolutions in the transition rate, transition dynamics. So in the quantum case, and let's suppose we have a state 0 for the left well and state 1 on the right well, and then we can write down as observable for the AB in the figure, which implies we are starting from 0, and then if there is a decoherence of the single qubit, single spins, and it ends up with the equilibrium state, like a 0 and 1 mixed state. And on the way, we can calculate the correlation, like a quantum time correlation function as a CT. So this is a kind of a spatial correlation function you can think of. And if T is 0, then there was nothing in the state 1, for example, and it gives a 0, as you can see on the left side, and then it ends up with some numbers at the end. But we are not interested in this case to compute the correlation functions. We'd like to compute C dot T directly using quantum computer. So C dot T is actually onto the theta B hat, which is observable in the B side, and with a time derivative form. Okay, before we go for, let's recap a little bit of Heisenberg pictures and Schrödinger pictures. Then I will explain why. And if we are interested in the expectation value of the observable in time t, we can think about this kind of a method. So psi t implies the states are having time evolution, time dependence. But if we write down at the end one, we actually put this time dependent onto the operator. So this is called the Schrödinger picture. If we track the time evolution in the states, and we call the Heisenberg pictures if we put this time dependent on the operator observable in this case. So if we are having unitary operation with a Hamiltonian, then they are a little bit different between the Heisenberg and Schrödinger pictures. And this is a closed system. So if we have the coherence, like a Lindblad terms, it's a little bit different from this side. The reason why I'm saying this is that we found two different schemes for computing transition rate. So this case is a Heisenberg picture case. So you can see there are controlled qubits and theta B observable, theta A observable, and then quantum equilibrium states. We put this as input states, and then we are performing the operations, and this is a kind of similar controlled N, controlled M, and then this controlled swap gate twice, and then we only measure again the controlled qubits, single qubits. And the main point is if you look at this C dot T, this is the part you can split, decompose by these different terms, and we can compute these all different expectation values when we change the n hat and m hat, for example. So at the end, what we have is a C dot T as a sum of the expectation values and denominated by epsilon D, which is the expectation value of theta A hat. And as you see, this is a Heisenberg pictures in the time evolution part for B. So, and you can think about, we have one qubit and L qubit, L qubit, L qubit. So overall, we have a 3L plus one qubit we required. So if you'd like to investigate 30 spin systems, for example, we have like a 91 qubits we require to perform this transition rate, for example. And as I said, we found the other way around, the Schrödinger picture case. And this has a little bit advantages if you look at for the first time, because we don't have theta A, which implies that we have only 2 times L plus 1 qubit. But there is a little bit of catches to make it, because we need to implement controlled projector, which is kind of non-trivial in the quantum circuits. And also in here, we adopted the ideas of a Cliff and Wang's the Lindblad time evolution circuits as a modular circuits. And then we need like expectation values of 5 terms, for example. And if we are calculating this one, we can get the expectation, the C dot T part as equivalent to the Heisenberg picture case. So I will give you 2 examples from now, which we investigated. So example 1 is we are having open spin half systems as a simple case, because this gives us analytical solutions for the C dots and C. So in physics sense, we have spin, and we put magnetic field, and then that's like a Hamiltonian mu sigma y. So it makes a rotation along the y-axis. But we have like a Lindblad forms for the sigma z, so like a projecting onto the north pole or south pole. And then if we are running these ones, and these blue lines are the analytical case, and this cross line is a numerical result. using the quantum circuits. And it matches at the beginning quite well enough. And if we see the plateau, and that is like a transition rate in this case. So we end up with a state 00 plus 11, as I explained. And we also had the opportunity to use IBM qubit as experiments. So there are different setups for this one. And the middle part is Lindeblad time evolution. And once we are performing it, we got the data like this. And we can also calculate the expectation value itself. And as you can see, there are little bit larger variations, even though we performed twice of the shots for the experiments. But then a C.T case, we have a pretty much narrower error bars. And then it's a kind of a good match with theories and analytical case. And we found that there is a little bit of gaps at the beginning without time evolutions. So if we are making a systematic error mitigations, and it's quite close to match the ideal and analytical solutions for these simple cases. And now I have not much time, but let's focus on the important case. So we also examined quantum Brownian motions in the 1D double wells, as I explained, and we'd like to focus on the short range of the time evolutions. And this is the potential that we are working on. And this is given by called the Caldera-Leggett master equations with positivity of density matrix. So Hamiltonian is quite different. And you can search for these papers if you're interested. And what we have done is numerical simulations with a 5-qubit density matrix, which is a 32 by 32 matrix as a systems. And we use the 16 qubits for the Heisenberg picture, and we can use the 11 qubits for the Schrödinger picture circuits, but we need to find how to implement the controlled projector gates. So this is a solution at the end, answer for this simulation. So we have a narrow reason for the A, which is observable, and the B is observable. So we try to find the transition rate between these A areas to the B areas. And it shows kind of quite good matches in the small t's, and there is a little bit of a divergence at the large t's because of we need a really fine, small time evolution steps if we would like to interest in the large T. However, we can see this kind of phenomena, which is a small quantum fluctuation in the C.T between the T's 1 to 2. And this is actually a signature of the rapid relaxation of the initial prepared state as non-equilibrium states in the well 1, well A. So that's a kind of brief ideas what we can do in the futures for maybe in the 2D of the Caldera-Leggett case, maybe. So thank you for your attention, and this is my colleagues. Thank you.
Is there any question? No? Then,
Thank you for the nice talk. Actually, I have a question not for the later part, maybe the topic of your research, but for the previous about the algorithm to find the steady state of the mastication.
Yes.
Could you show me the slide once more?
Yes. So let's go back to This one, maybe?
Yes.
Okay.
Maybe I think I understood the concept to get the expectation value. It is also important to the later part, but how can we get the steady state which makes the expectation value 0?
So if we prepare the raw T, and then we put this raw T into the quantum circuits, like underneath one, and I think I had a little bit of a rush to explain this one. But for example, if we are having like variational approaches,
Yes.
we change the raw T with the knobs, like controlled parameters, and then it will give us some numbers in the expectation values. And not only one expectation values, you need at least 3 terms of expectation value adding together. If it gives a 0, then we change the T. We can control the T in the systems. And then once this, so this is not just a straightforward finding the steady state at once. It's like an iterative variational algorithm you can think of,
But
in a sense.
But it seems like a 0 is not the minimum expectation value.
No. This is the representation for the on the left side of the thing. So d over dt, rho t, expectation value is 0. So even though I change the t, I still get the O0, and then this is the steady state solutions we can think of it. So there is a papers we can discuss maybe more if you want.
Okay, thank you.
Okay.
That concludes the presentation. This marks the end of our session. Thank you for your time and have a great day.
Okay, thank you.
안녕하십니까. 연세 퀀텀위크 2025 안녕하십니까. 연세 퀀텀위크 2025 인더스트리 세션에 참여해 주신 모든 분들께 진심으로 감사드립니다. 여러분의 관심과 열정 덕분에 연세 퀀텀위크 2025 인더스트리 세션이 풍성하게 마무리되었습니다. 내일 이어지는 국제 컨퍼런스에도 많은 관심과 참여를 부탁드리겠습니다. 모두 안전하게 귀가하시길 바라겠습니다. 감사합니다. Ladies and gentlemen, we sincerely appreciate your participation in Yonsei Quantum Week 2025 Quantum Industry Session. Thanks to your enthusiasm and engagement, the Quantum Industry Session has been successfully concluded with enriching discussions. Thank you once again for being a part of Yonsei Quantum Week 2025 event. We wish you all a safe journey home. Thank you.